What's up, everyone? This is Mrs. Sharp. Want to give a big shout out to all our band peeps cruising out to New York, missing school Thursday and Friday, but it's all good because we got your chemistry notes on lockdown. 5.2 coming at you. Those of you who are not going to New York, hey, you can watch too, get something out of it. Maybe you were absent, or maybe you just thought it was super cool and wanted to hear it all again. I don't know. Anyways, here we go with learning target 5.2. Go ahead and read you the learning target here. We are going to describe how and why ions are formed. We're going to predict what kind of monatomic ions certain atoms on the periodic table would form after gaining or losing electrons based on the number of valence electrons they have. So a lot of repeating stuff from last unit in there. Also, we're going to explain what is meant by a polyatomic ion and describe the number of electrons these ions contain. If you need more information, section 7.1 in your book is the place to go, or you can come see me, of course. So here we go. How and why are ions formed? All ions are formed when neutral groups of atoms or groups of neutral atoms gain or lose electrons. So remember, neutral meaning no charge at all, and if I gain an electron, I'm going to be getting a negative charge. That's an anion. If I lose electrons, that's going to give me a positive charge, which we call a cation. And we've talked about this a lot before, but we've really basically said we've been talking about an atom, but we haven't really been talking about groups of atoms. So that's where we're going to make this differentiation between monatomic, which would be a one-atomed ion, or a group, which is called a polyatomic ion, which would be anything that's more than one atom. So the charge, I want you to know, is sometimes called its oxidation state. On your periodic tables, the charges that are written in there are called oxidation states. Now, it's not technically the same thing, but for our purposes in this class, we're just going to assume that they're the same thing. So if there's a +3 charge, it's also known as that atom has a +3 oxidation state. Let's talk about monatomic ions first. These are single atoms forming ions, so something like what we've been talking about, like S-2. That's monatomic. It only has one atom, and the atom is sulfur that has gained 2 electrons. That charge is based on the number of electrons gained or lost found by the number of valence electrons. So sulfur has 6 valence electrons. It will gain 2 electrons to give it its -2 charge. We're going to look at the charge of the family because remember, a family on the periodic table is a column. Everybody in the same family is going to have the same number of valence electrons. So let's say 2. Every single element. So if every single element has 2 valence electrons, every single element is going to form an ion that has a +2 charge. To name ions, for positive ions, we name them the same as the name of the element. For negative ions, we use part of the element's name and then it ends in "ide." So F-1 ion's name would be just fluoride. Let's talk a little bit, go back and talk about why atoms form ions. We've talked about this before, but just as a double check, it's super important. Let's take aluminum, which has 13 electrons total, and write its electron configuration. Whoop! There it is. 1s2, 2s2, 2p6, 3s2, 3p1, which means it has, dun 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 dun, 3 valence electrons, right there. So 3 valence electrons, 1, 2, and a third in the third energy level, shown by the big 3 there, which is not a stable configuration. We've learned that 8 is the most stable, or a full valence shell, and 3 is not full. 8 would be full. We don't have 8. So what we can do here is we can either gain 5 more in the third energy level or lose these 3 so that we would have 8 in the second energy level. So aluminum's going to lose 3. If it loses 3, it has 10 electrons, giving it a +3 charge. It also gives it an electron configuration of 1s2, 2s2, 2p6. Now, aluminum has 8 valence electrons, right there, and 8 valence electrons makes it the same as neon. It has 10 electrons total. 2 plus 2 is 4, plus 6 is 10. An 8 valence electron. This aluminum ion thinks it's neon, but it's not. So aluminum gained or lost, in this case lost, electrons to become like a noble gas. It has an electron configuration that's like a noble gas, but it's not a noble gas, so we call it a pseudo-noble gas notation. I want you to mark up your periodic table a bit. Here is a nice blank periodic table. You have your big periodic table. I'd like you to mark that up a little bit. And the first thing I'd like you to do is pick a color or a pen or something, and I'd like you to mark in valence electrons. So take a color, and I want you to mark in that everybody in this family has 1 valence electron. Everybody in this family has 2 valence electrons. Everybody in the transition metal has 2 valence electrons, but we're going to skip that. Everyone in this family has 3, 4, 5, 6, 7, and except for helium, 8. Now let's go ahead and based on that write in the charges of all the elements in those families. So I'm going to use green to do that. If I have a 1 valence electron, so I better go and make a key so I remember what I'm doing here. So blue equals valence electrons. And I'm going to use green for ion form. So if I have 1 valence electron, I'm going to form a +1 ion. I'm going to circle that. If I have 2 valence electrons, I'm going to make a +2 ion. All of the transition metals are going to be positive, and remember we said that they vary in charge because of those stinking D electrons. 3 is going to be a +3. 4 is going to be either plus or -4. 5 is going to be a -3. We're going to switch over now and start gaining electrons. 6 is going to be a -2. 7 is going to be a -1. And these noble gases are not going to form an ion. So now on our periodic table, we should be able to quickly look at these 2 blocks of elements, your S and your P block, S and P, or your representative elements. Whoopsie. Little pen issue here. Representative elements. And we should be able to look at our representative elements, quickly go to the top of that family and see the number of valence electrons and the charge of that family. Let's talk about polyatomic ions. And for polyatomic ions, the important thing I need to mention here is that you need to see your list that I gave you. At the top it says common ions. And I gave you this sheet on the day that you took your pretest. It's just kind of a one-sided sheet with a list of ions on there. And this is many atoms bonded together as a group. Remember, more than one atom makes it polyatomic. So a polyatomic ion might look something like this. This is the hydroxide on your sheet. They are in alphabetical order, so if you go down to the H's and find hydroxide, you'll find OH minus 1. Now what this means is that the OH are stuck together. So I kind of think of them as in this bubble. And overall they have a charge of -1. So if you need to know how many electrons these guys have, they have oxygen 16, they have hydrogens 1, and they have 1 extra from the electron. So overall there are 18 electrons here. S2O3 is also in a bubble. This time I have, let me go back here for a second. In this polyatomic ion I had 2 atoms. 2 is greater than 1. So it's polyatomic. Here I have 1, 2, 3, 4, 5 atoms. So that's what makes this polyatomic. So in this case, this is the thiosulfate ion. If you go down to your T's, you'll find that this is thiosulfate. Whoopsie. Thiosulfate has a -2 charge. And it has, let's see, it has 16 for one sulfur, 16 for another sulfur. It has 8 an 8, and 8 for each oxygen, and then the 2 electrons extra for the charge. So that would be 32, 40, 48, 56, 58, if I did that right. Which means I actually did this one wrong because I said that this was 16 when oxygen's 8. So really this one would be 8 plus 1 plus 1, so that would be 10. Let's see, 32, 40, 48, 56, 58, yep. So those extra electrons just add to the overall number of electrons. We don't know if those extra electrons are floating around we don't know. We just know they're extra. So those are polyatomic ions. The last group we want to talk about are monatomic ions that are also transition metals. So in other words, those ones that we said varies earlier in the D block, that we said they are positive, but they vary. So they're always positive. You're going to use the black numbers above the symbol on the periodic table. So if you look at those, it's going to look something like this. You will see, let's see what's a good one. If you look at silver, silver is Ag, and right above the Ag symbol, you will see very small, a black 1. And that's its charge. So silver's charge is going to be a +1. Now some elements have several numbers, and the bold would be the most common of those. So for example, you might have an element, let's say you have, oh gee golly, let's say you have cobalt. And I don't have this memorized off the top of my head, but I think you could have a cobalt 2 and maybe a cobalt 3. And so a cobalt could vary in charge. It could be +2 or +3. But perhaps the 2 is a little bit bolded. So that means the most common is +2. But it could be +3. For naming purposes, when we start to name compounds, you need to highlight what we call the magic 6. And the magic 6 are the following, and on the next slide I'll help you with this, but the magic 6 are chromium, iron, copper, tin, mercury, and lead. And those are considered magic because they, in our class, are not going to have a most common. Their charge is going to be denoted by this weird suffix term, ik or aus. So ik being the higher of the two charges, aus being the lower of the two charges. So let's switch over to our periodic table and I'll show you what I mean. So let's go ahead and highlight those 6, our magic 6. So I'm going to take yellow and I'm just going to fill in the entire box for, whoa, let's try that again. Let's use yellow. So I'm going to highlight the whole box for chromium 24, for copper 29, whoops, I skipped iron 26, skip down to tin number 50, mercury, and lead. Those are your magic 6. So I'm going to do a little key there. So for your magic 6, the ik is going to be the higher of the two charges, and the aus is going to be the lower of the two charges. So for example, if you look at copper, above copper symbol, you will see a little 1, 2. So what that means is copper can either be +1 or copper can be +2. Now the lower of those two charges is +1. So that is the copper aus ion. Copper +2 is the higher of the two charges, so that would be the copper ik ion. Same thing with, let's do, what do I have room for here? Let's do lead. Lead has a 2 and a 4. So Pb aus would be what? Aus means lower of the two charges. In this case, the lower of the two is plus 2. So the Aus ion for Pb is plus 2. For lead, the Ich, the higher of the two, is plus 4. So the Pb Ich ion is plus 4. Now this Ich and Aus rule only apply to these 6 elements. Well, I hope you enjoyed that as much as I did. I sure hope that you have a really, really good day. I hope you enjoyed learning about ions, and I will see you later. Okay. All right. You know what? Hey, I gotta quit this. I gotta get out of here. I gotta stop this. All right.